in this mathematical induction example, I thought we might do something a little bit different, and just to show you the power of mathematical induction. So the claim is that if you have n lines in the plane, such that no lines are concurrent, so I should explain what that means, such that no three lines are concurrent. So concurrent lines are lines that intersect at a point. So, any two non-parallel lines will always be concurrent because they're going to intersect somewhere. But if I have three lines, then they need not be concurrent because, for example, these three lines aren't intersecting at the same point. However, these three lines are concurrent because they do intersect at a single point. So the assumption here is we have n lines, none of them are parallel, and no three or more are concurrent. Okay, so now the claim is that the plane will be divided into half times n squared plus n plus 2 regions. Okay, so and this is supposed to hold for n greater than or equal to 1. So let's have a look at the base case. So with the base case, well, I've only got one line. It doesn't make sense to talk about if it's parallel to any other line because there's no other lines. And here, we've divided the plane into two sections. Okay, so let's see if our formula works. So we end up with half 1 squared plus 1 plus 2. Of course, this is 4 on 2, which is 2. So the base case does indeed work. So now we need the induction step. So suppose the claim holds for all n, where we allow n to go from 1 to some fixed capital N, which is greater than or equal to 1. Okay? So we have all these lines in the plane, only drawing some of them, and they're dividing the plane into all these different regions. So what we do is we remove one line. Okay? By the induction hypothesis, which is this line, so by the induction hypothesis, the plane will be divided into half times this capital N squared plus n plus 2 regions. Now we put that removed line back. Okay. And what's going to happen is we have already these n lines. So let's see if I can try to fit them in here. So, maybe this is line 1, this is line 2, this is line 3, this is line capital N. And when we put this new line back, say this line here, n plus 1, well, what's it doing? It's going to intersect with these lines, well, n times, okay? And so it's actually making 1, 2, 3, and down here, I guess, this would be the nth region, and underneath it would be the n plus 1th region. So by adding this new line, we create n plus 1 new regions. So put the line back to create n plus 1 new regions. So what will this mean? All right, so now the total number of regions was this, which we had before. And then to this, once we added that line again, we've created n plus 1 new regions. Okay, now I can factor out a half, so let's multiply this by 1, factor out the half, and then inside here we have n squared plus 3n plus 4. So we want this thing essentially to look like this first term where n plus 1s replace the n's. If that happens, then we will have completed this induction. So what I can do here is I can take 2 of the n's and 1 away from this constant 4. I can do that. I've still got 1 n left over, so let's put it here. I've already taken 1 away from the constant. I might take another one, and then there's going to be 2 left over. So indeed, this is the same formula as at least this part, with n replaced by n plus 1, and so this completes the induction.